Me. I will. You won't do it. That's no sense, or you know, that's good.
All right, it's 4 o'clock. Let's go and get started. Let me just check. Okay, looks like it's going. All right, so good afternoon, everyone. How's everyone doing today? Good, good. All right. Yeah, I was telling a class earlier today that I always think that this week, I think out of all the weeks that we do in in the semesters, I think this is one of the hardest because we've been going at this for this is our 13th week in a row of just straight instruction with no days off, and we're right before Thanksgiving. So I know everyone's tired. I know everyone's really stressed, especially in this class. I know we have a midterm Thursday, but but Thanksgiving's almost here, so that's something to look forward to. Okay, so for this class today, we're going to continue where we left off on last Thursday. And so we were talking about muscle force optimization. And so we'll dive a bit more into it today. We'll do an example today to kind of show you kind of, what this is all about. And then we'll go from there. Okay. Announcements. Remember, our midterm exam is this Thursday. So remember, it's an in-class exam. And so you'll have to be here in person. Just like the first midterm, you're allowed to bring a writing utensil, calculator, cheat sheet, and for the cheat sheet, you can write on both sides. You can write it, you can type it. It doesn't really matter to me. And we'll take it over the course of the lecture. Yesterday, I recorded a review video. I posted on YouTube. I forgot to send it to you guys. So this morning, I sent an announcement to the class with a link to the review video. So make sure you check that out to help you study. I try to cover as much as I could. So I went through all 4 of the main topics that we covered. That's going to be on the midterm. Muscle force optimization is not going to be on the midterm, so you don't have to worry about that. But everything all the way up to inverse dynamics is going to be there. Homework solutions. I know I'm quite a bit behind in grading the homeworks, and so I know you guys have submitted and turned in homework 4, and homework 5 is due tonight. And so what I'm going to do tonight is I'm going to post solutions to both of those. Even though I haven't graded homework 4 yet, I'm really behind on that, and so I'm probably going to grade that over the next couple of days. But I at least wanted to make sure that you guys have the homework solutions available to you, so you can use them as a tool for you to study. Okay, so both homework 4 and homework 5 solutions are going to go up tonight. Homework 4 probably as soon as I get back to my office, and then homework 5 closer to when it's due, probably right before I go to sleep tonight. I'll put homework 5 solutions. Okay. All right, and so that's all my announcements. Are there any questions I can answer before we get started for today? Yep. Yep.
You want us to show where the cross product or calculators to do it? Is that allowed?
If your calculators can do it, I would at least want you to show me that you set it up, and then say maybe indicate there that computed this in the calculator, and then you can just put the result there. So that's fine with me.
What do you mean set it up? You mean
Just show me the 2 vectors, and so just say I want to take the cross product of this vector cross with this vector, and then you can put an equal sign, and then next to the equal sign you can say I computed this in a calculator, and then give me the result. That's fine for me. Yeah. That's a good. I have another follow-up point on that too. So for this upcoming exam, I know one of the probably the more time-consuming things is performing the matrix multiplication for the transformation matrices. And so I wrote the exam this morning, and so you're not going to have to do that on the exam. And so on the exam, you're gonna have to do cross products, and so you're gonna have to form transformation matrices based on X and Y axes for a 2D problem. But you're not going to have to perform any matrix multiplication, because I think that's just kind of time consuming, and it doesn't really test what I want to test on. And so you'll have to set it up, and so you have to show me that in order to get these matrices you would have to multiply them, but you don't actually have to carry out the multiplication. Okay. Yeah.
So what you're talking about right now is basically, let's say we're finding the Y vector with the cross product with X and Z, so just do X across Z.
Exactly. Exactly. Yeah. And so if you want to reference, it's the question about inverse kinematics on the exam is going to be very similar to problem 2A on the homework. And so 2A part 1, 2A part 2 are definitely fair game for the exam. 2A part 3, I would ask you to set it up. I wouldn't ask you to actually perform that multiplication. And then 2A part 4, you should understand conceptually kind of what's going on there. So that's going to be the gist of that problem. I got a couple of questions about it over the weekend, and so I wanted to make sure I I want to be clear about kind of what I'm expecting for that. Okay? So you should definitely understand conceptually what you're doing, but all the nitty gritty kind of tedious calculation stuff, you don't have to worry about that for the exam. Okay. All right. Any other questions for about the exam or anything else? Okay. All right. So let's go ahead and continue on. Right, and so we're talking about muscle force optimization. Okay. So, it's a little bit of a shame that I didn't get to put this in before the midterm exam, because it really is kind of the last piece of the puzzle. And so, everything that we've done in human dynamics, this is kind of the very last step. And so, because ultimately, remember, our goal when we first started out with human dynamics is that, as a person goes through a motion, we want to find out exactly how much force each muscle is exerting to produce that motion. And so we know that in our body is comprised of all these different muscles. And when they kind of act in unison, they produce the beauty that is human movement. Okay. The problem is, up to this point, we've only covered up to inverse dynamics, right? And so with just inverse dynamics alone, that's not enough information to tell us how much force each individual muscle is exerting. Okay? And so the only thing that inverse dynamics gives us is the net amount of force and the net amount of moment that has to occur at each joint. Okay? Okay. And so with that information alone, that's not enough to tell us, to break it down per muscle. Okay? And so in other words, say we have a situation like this, okay? And so let's say that this arm is going upwards like that. Okay? All we know so far from inverse dynamics is that there has to be, maybe a net force this way. And so everything in red here, those are the net forces and net moments needed to produce this action of a simple kind of, dumbbell curl here. Okay? But we don't know how to break that down in between each individual muscle because, what we've seen kind of multiple times that at this, at the elbow joint here, we have one muscle, we might have another muscle, we have a third muscle. Okay. And so what we want to ask is how the work is broken down between the three muscles. And so if you look at a situation like this, visually, what you basically are seeing is that you have three muscles that in the end kind of produce the same action, right? And so they all can contribute to flexing the elbow, right? And so there's a lot of redundancy in the human body, which in general is a good thing, right? And so you want redundancy in systems like this, so that if one goes down or if a situation occurs, then there's kind of a fail safe. There's kind of a way for the body to kind of adapt to multiple situations. Okay, but this redundancy also makes it very difficult to solve, just because there's kind of too many unknowns for the equations that we have. Okay? Because normally in a situation like this that we've dealt with up to this point, we have an equal number of equations to solve for the number of unknowns, right? So let's say that we have 6 unknowns, we would be able to generate 6 equations for that. Okay, and so the types of problems that we are solving for now, where we have kind of more muscles than equations, then we can't solve it with traditional methods. And so the way that we have to solve these is through optimization. So like I mentioned last time, optimization, it's a very broad class of algorithms. And so it's, you kind of need a whole class to get dedicated to them, to really kind of understand them. And solving problems with optimization kind of requires almost like a totally different mindset. It's very different than how you solve problems traditionally. And so I think that's what makes them fascinating. But I think it also makes it incredibly difficult to kind of go over in kind of a short period of time that we have. So, I'll preface this by saying that, optimization, it goes very, very deep. There's a lot of different nuance and a lot of different ways to accomplish it, a lot of different theories, and it's very much an active area of research nowadays. We're going to cover kind of the bare basics in terms of how you set one up and how you actually use a built-in optimizer. And so we'll talk about how to actually use the optimizers that are in MATLAB. But we're not going to go beyond there. Okay. All right. Any questions on any of this? This is just kind of a recap from last time. Okay. All right. So let's talk a bit more about optimization concepts and optimization terminology. Okay. And so, like I mentioned, optimization is a very different way of looking at solving problems. So I think what we're traditionally kind of taught and what we traditionally kind of know just in general is that we have to have the same number of equations as the number of unknowns, right? So that's traditionally how we solve a lot of these problems, either in an algebraic way or even in differential equations as well. Okay. So for optimization, it's a lot more broad. So you don't have to have, you really actually don't even have to have equations in general. You can actually do optimization without any equations, except for one you can make up. Okay. And so the only requirement, in order to run an optimization, is you need to have a way to check how good a candidate solution is. Okay. Okay. And so the paradigm kind of shifts in terms of how you actually, come up with a solution through optimization. Instead of, solving a set of equations and kind of solving for the best solution based on the equations, it's a lot more of a guess and check kind of paradigm. And so the way it works is that you kind of present a solution, you check the solution. If the solution is good, you say, this is good. And then from that solution, you kind of go back and you say, how can we improve this solution? Okay. And so it's kind of a circular thing. And so I think it's best visualized with kind of a figure here. Okay. All right, and so we're going to start with a vector x. Okay. And so I call it a vector because this right here, I like to call our candidate solution. So this is basically something that we're proposing as a good solution. Okay. So this is our guess. Right. So what we do is we take this candidate solution, we run it through our checker. Okay. And so what this does right here is that this checks how good the solution is. And so we'll call that some function f of x. Okay. I'm giving it a mathematical form here, but again, it doesn't have to be a function. It could be just kind of intuition. Okay. After you check the solution, you're going to evaluate and see how good it is. Okay. After you evaluate the outputs, you're going to come up with a way, you're going to ask yourself, is there any way for us to improve the candidate solution kind of based on the outputs? And then from there, you're going to go right back to it. And so after you improve the solutions, you're going to run it through the checker, see how good it is, evaluate it, improve it, check it again. And so it's very much like a cyclical kind of iterative guess and check. Okay. So that's how optimizations work in a nutshell. Okay, and so it's again, it's very different. And so it's not like you're solving for, it's not like you're solving a set of equations for the solution right away. It's something that you're kind of continuously guessing and checking. Okay. Of course, you know, a real optimization algorithm is a lot more sophisticated than a guess and check, but you know, because you're not just guessing, you're not just guessing randomly, and you're not just improving randomly, right? And so, you know, there is logic to all this, and so, you know, how I'm describing it here, you know, I think hardcore optimization people would be kind of insulted based on this model here. But I think, you know, the reason I kind of explain like this first is to kind of highlight how different it is. Okay. And so you may be asking, you know, how do you might be asking a ton of questions right now. So you might be asking, you know, how many guesses do we even do? How do we know that we've reached an optimal solution? You know, how do we actually improve results? And so these are all kind of, you know, all really good questions, and all things that are kind of specific to, you know, whatever algorithm that you're using and what the goals of your optimization are. So you can see it's a very general framework, and you can apply it to a lot of things that aren't strictly engineering stuff at all, right? And so, you know, and in fact, you know, I would say that you probably go through this process in some way or another throughout your life, throughout your daily life, right? And so I'll give you an example, kind of a silly example, but it's one that I've personally done and have not found an optimal solution yet. And so let's say that you're trying to solve the problem of finding an optimal combination of pizza ingredients that will satisfy both you and your partner. And so you can apply our optimization algorithm or our optimization kind of framework here to solve this problem. Okay. And so let me go ahead and label you know, everything in our diagram here, and I'll tell you how they kind of correlate here. Okay. All right, so first we have the X vector. So remember the X vector, those are our candidate solutions. Okay. Another name for them that I should have given up there is the design variables. And so the the point of the X vector is that this contains the collection of all the variables you can change in your problem. Okay. Let me just erase this down here for a second. And so for our pizza ingredient problem here, the variables that we have control over are the pizza toppings or pizza ingredients. And so I use the term design variables here, but design variables is the same thing as candidate solutions. Okay? In other words, X vector here, that represents the things that we can change about our system to kind of change our results. Okay? All right. Now we have f of x vector. Okay? And so from the figure above, you said I said this was kind of a way to check your results. Okay. And so another word for this is we call this the model. And what the model is basically most of the time, and for our muscle optimization problem, it's going to take a mathematical form. But the model is basically a way for us to basically take a set of design variables, take a set of candidate solutions, and assess or give it a score of how good that solution is. Okay. Okay. And so for our pizza problem, our model here is, how do you test and see how good a pizza is? Well, you eat it, right? Okay. Right, so this is a good example of a problem that you can solve with optimization because there's no formula, right? There's no taste bud formula that's going to tell you, if you have this combination of pizza ingredients and this exact ratio from this exact supermarket, aged by this amount of days, there's nothing like that. And so the only way to tell if a pizza is good or not is to put some ingredients on a pizza, cook it, eat it, and see if it's good. Okay. And of course, you're not going to find your favorite pizza the first time that you make it, right? And so you're going to try, maybe you're going to just try a straight up pepperoni first. You make a pepperoni pizza, you eat it, you're like, that's all right. And you put, and then you maybe try another ingredient, and you put pepperoni and sausage. You make the pizza, you eat it, you're like, hey, that's pretty good too. Okay. Maybe your wife says, like, I think pineapple is a good ingredient on pizza. So if you cook pizza with pineapples, it's disgusting, you hate it, and so no more pineapple on pizza, right? And so it's an iterative process, just like this, okay? All jokes aside, pineapple is fine on pizza. I used to be a very big, I hate pineapples, but my wife likes it, so I guess I like it now too. All right, any questions on this so far? Okay. Okay, so let's talk a bit more about optimization kind of concepts. And so there's a couple more things that we need to define here, before we can kind of jump back to muscle stuff. Right. So the first term I want to describe is something called an objective function. Okay. And so an objective function is basically a mathematical form for f of x vector. Okay. So remember, for any optimization algorithm, there has to be a way for you to assess how good your solution is. Okay. And for most optimizations, at least the ones that you're going to run in like MATLAB or Python, you're going to do that through an objective function. Okay. And so the objective function is some mathematical function. And so it's one that you define. Okay. And so whoever is running the optimization algorithm, you have to define what that objective function looks like. And ideally, that objective function should be one where, it's able to give a certain score to certain candidate solutions. Okay. All right. So for most optimizations, especially the ones that you're going to be kind of making yourself, we're not going to do too much in this class just because the class is kind of winding down. But if you were to kind of pursue optimization more, an objective function is kind of a must. Okay? Sometimes these are called penalty functions, and those work just a little bit differently. But the kind of the terminology that I use and the one that I see kind of most often is objective function. Okay? Okay. Another thing that we have to define is constraints. Okay, and so constraints, these are restrictions on particular values of the candidate solutions that can't be violated throughout the algorithm. Okay. And so constraints are really important. And so, the thing about optimization algorithms, especially if you're using like a pre-built one in MATLAB or something like that, you actually have very little control over how it's going to be. And so, the way it kind of works is that you're basically going to set up the problem, you're going to define the objective function, and then you're going to say go, and then MATLAB is going to churn for like 30 seconds, and then it's going to spit out the solution. Okay, so you have very little control over what the optimization does, which is kind of nice for some cases, but also a little bit scary for some cases too. Okay, and so to kind of make sure that your candidate solutions don't give you any kind of unrealistic values or unreasonable values, you can put constraints on them. Okay, and so for an example. Okay? And so one example that we are going to do very soon for the for the muscular forces is we want to make sure that the muscles can only contract. Okay, and so what we learned is that muscle can only contract and so can only provide a tensile force. Okay, Because it could be that if you don't constrain this and you run your optimization algorithm, the optimizer might say that, the optimal solution is for your biceps to do a compressive force. Okay. And that's just physically impossible. Okay? Because of how muscles work. And so to make sure that that doesn't happen, you can place constraints on your design variable so that you don't kind of get that. Right. Another example for pizza, maybe you put constraints to say that you can say absolutely no pineapple on pizza. So you put a constraint so that, no matter what ingredients you pick, pineapple is never going to be one. Okay. Okay. Any questions on this? All right. And so now that we kind of have an idea of how these optimization algorithms work, we've been introduced to the terminology. We're ready to kind of formally introduce how to actually set up an optimization problem, or the formal definition, the formal kind of declaration. Okay. Right. So with all these definitions, okay, the formal optimization problem looks like the following. So what we aim to achieve is we want to minimize our objective function. Okay. And so we want to find the value of design variables that minimizes our objective function. Okay. Okay. Usually we want to minimize, and so you'll see soon that we form our objective function so that when that is at a minimum, then that is our optimal solution. It's possible to alter a optimization algorithm to maximize, but generally a minimize is more stable and kind of more standard. Okay. All right, so that's our goal. So our goal is to minimize our objective function, but we are going to subject our candidate solutions here to some constraints. Okay. And so we can formalize our constraints to a function like this. Okay. And so if we say gi of x vector is less than 0, and so we call these inequality constraints. So that's one type of constraint that you can have. You can also have equality constraints. And what we can also do, and this is most common, is we can specify bounds. And so we can say that our design variables are they're limited to just this particular range. And so this is kind of the formal statement of an optimization problem, okay? Okay. And so to solve an optimization problem, there are ways that you can do it by hand. And for very simple problems, you can do that by hand. But for most practical optimization problems with at least 2 or 3 or 4 or 5 different variables, you're going to need a computer to solve it for you. Okay. And in fact, you're going to do very little solving yourself. And so what you'll see is that in order to solve an optimization problem, all you really have to do is just kind of set it up. And so you have to define the problem and in a way that the computer can understand, and the computer will take it from there. Okay. Any questions on any of this so far? Okay. All right, so that's kind of an aside, and so that's kind of how optimization works in general. Let's kind of bring this back to biomechanics. Okay, so let's talk about how we can actually apply this to solve our muscle problem that we have. Okay. Okay, and I think this is kind of best illustrated with a more concrete example. And so we still need to learn how to actually apply this optimization in general to biomechanics. But I think it's I'm going to do kind of a long worked out example that's going to show you how this is done. Okay. But before I do that, I'll say that remember what we're looking for is we want to based on kind of a net moment or net forces produced at a joint. We want to find out how the individual muscles can produce that moment. Okay. For example, all right, so let's say that we conducted our human motion kinematics, and so we did a motion study. Okay? So we have the kinematics. We did inverse dynamics on that, and what we found from inverse dynamics is that there is a net moment of 100 Newton meters being produced at the ankle in plantar flexion. Okay? So that's the net moment that we're working. Okay. Our next step is to find out how many muscles do we have at the ankle that can help produce this moment. Okay. And if you look at kind of a diagram of the muscles in the lower leg, you'll see that there are 5 muscles that can act on the ankle. And so 3 of these muscles are plantar flexors, and so they produce that plantar flexion moment. And the other 2 are dorsiflexors, and so they produce moments the other way. All right, so the first muscle we have is called the gastrocnemius. And for each muscle, I'm going to list out the maximum amount of force that they can produce based on their cross-sectional area, as well as their momentum. And so for the gastrocnemius, the maximum force it can output is 4,097 newtons. And its moment arm is 3.9 centimeters. The second muscle that can produce a plantar flexion moment is called the tibialis posterior. And so the maximum amount of force the tibialis posterior can exert is 3,052 newtons. And its moment arm is 0.8 centimeters. Okay, so it's very close to the joint. And the third muscle is called the soleus. And the soleus muscle has a maximum force of 6,435 newtons and has a moment arm of 3.6 centimeters. Okay. Okay. So those are the 3 plantar flexors, and so those can produce plantar flexion moments. Let me list out the dorsiflexors. So there's 2 of them. So the first dorsiflexor muscle is called the extensor digitorum longus. Yeah, I giggle a little bit when I read that name too. Okay, so the maximum amount of force that this muscle can produce is 801 newtons, and its moment arm is 4.2 centimeters. And the other dorsiflexor muscle is the tibialis anterior. This has a maximum force of 1,207 newtons, and its moment arm is 4.5 centimeters. Okay. So a lot of data there with kind of long names, but that's kind of what we have. Okay. So we have 5 muscles, right? And so we know the maximum amount of force that they can each produce. But for a simple moment of just 100 Newton meters, that's fairly small. And so, it's, not all of them are going to be maximally activated. Okay. And so we have 5 muscles here and only 1 moment, right? And so, this is a good example. So we have 5, basically 5 unknowns and only 1 piece of data. So the only data we have is that we need 100 Newton meters of a moment, and we have 5 muscles that can do it, right? And so to produce a moment of 100 Newton meters, there's lots of different ways that we can do this. In fact, I would say there's infinitely many different combinations of the different muscles that can produce 100 Newton meters of planar flexion moment. Okay. And so there's infinitely many, ways that we can satisfy that condition. Okay. Just like there are infinitely many different combinations of pizza ingredients too. And so the only way that we can solve this is if we use an optimization algorithm. And so in this problem, what you'll see is that, you'll see, I'll demonstrate how to take a kind of a biomechanics problem like this, how to formulate it in terms of an optimization problem, and then how do we actually set this up in MATLAB for us to solve. All right, any questions on this so far? Okay. All right, and so our next objective here, or our next goal is to say that, how can we take this problem and then put it in a way that an optimizer or an optimization problem could be solved. Before we do that, I'm going to simplify some things a bit, just to kind of help simplify the solution. Since we know that we need a planar flexion moment, for this first part here, we're going to assume that the dorsiflexors are dormant, or they're not going to contribute. Which makes sense when you look at it from a purely numbers point of view, right? And so if the goal is to get 100 Newton meters of planar flexion moment, then it doesn't make sense for us to produce a moment in the opposite direction, because that's not going to get us closer to the goal, okay? In reality, it doesn't actually work like that, because whenever you produce any kind of motion, usually the antagonist muscle, or the muscles that produce the opposite motion, they're engaged somewhat just for kind of balance purposes, okay? But for now, we're just going to ignore them. And so we're going to ignore these 2 muscles here, okay? And we're going to basically simplify our problem to just looking for 3 muscle forces. Okay. And so let's go through all the different parts of the optimization problem, and let's define them in terms of this problem here. Let's start with the design variables. And so remember, design variables, these are the parts of the problem that we have control over, that we can modify in order to change our objective function. Okay. And so in this problem, our design variables are the magnitudes of each of the different muscle forces. And so I'm just going to list them out here. And so our first design variable is the gastrocnemius force. Okay. And we know the cap on this variable. We know that it has a maximum of 4,097 newtons. So we can immediately specify the bounds. And so we can say the gastrocnemius force has to be between 0 and 4,097. Okay. So next we have the tibialis posterior force. And so we'll give that the symbol FT. So now FT has to have a value between 0 and its maximum, which is 3,052 newtons. Finally, we have the soleus force, and then soleus, we'll call that FS, has between 0 and its maximum, which is 6,435. And so these define the upper and lower bounds for our design variables. We kind of did two things at once. So we defined what our three design variables were, and we defined what their upper and lower bounds were. So let's talk about constraints now. And so our constraint in this case is that no matter what combination of muscle forces that we solve for, they have to produce a net moment of 100 Newton meters. Because that's kind of the problem that we were tasked with at the beginning. Okay? And so we can constrain it. And so basically what this constraint says is that every guess that we produce, you want to make sure that that moment is being satisfied. Okay? And so we can set up a moment equation for this. And so we sum up the moments. Okay? We know this is equal to 100 Newton meters. And so this has to be equal to the sum of all the moments that are produced by the muscles. And remember, the way that we compute moments is we take the force magnitude multiplied by its momentum. Okay. So all these R variables here, these are the muscle moment arms. And we can go ahead and plug in for those because those actually aren't going to change. And so we can plug in for the muscle moment arms here. Okay. And so for our constraint, we say that we have 100 Newton meters. This is equal to 0.039, and so that represents 3.9 centimeters, multiplied by Fg plus 0.008 Ft. And so that 0.008 represents the moment arm for the tibialis posterior muscle. We have 0.036 multiplied by Fs, where that 0.036 represents the 3.6 centimeter moment arm for the soleus muscle. Okay. And so no matter what values that we solve for Fg, Ft, and Fs, this equation must always be satisfied. Okay. All right. Any questions on this so far? So we defined our design variables as well as a constraint on its values. Okay. Okay. And so all these, I think, both the design variables and setting the constraints, these are more or less straightforward. Okay, so these come kind of straight from the problem. And in fact, based on these are all kind of very, I call them deterministic. Okay? And so they're, we're always going to have equations like this. Okay. Now comes a little bit of the art that comes in an optimization. So now we have to define our objective function. Okay. So remember, with our objective function, we need a way for us to determine which combination of muscle forces is better than, say, another combination of muscle forces. And so that's the point of the objective function. And so I think this is the part which trips most people up with optimization, because this is something that you have to determine on your own. So you have to come up with your own objective function. Right? And so we have to basically come up with a way to say, what's the best way? How can we rate this? Right. And so how can we come up with this on our own? Well, it depends what we want to optimize, right? So really, you have to kind of decide, what's kind of the most important in our solution, and how can we kind of encapsulate that into a mathematical function. Okay. And so I'm going to do the same problem, and I'm going to do it a couple ways. And so I'm going to show you kind of how the choice of the objective function can affect our results. Okay. So let's do something that's very simple first. And so let's write an objective function that's going to minimize the raw total amount of muscle force that we're going to produce. Okay. And so the raw total amount of muscle force could be just it's just the sum of all three. Okay. And so if we say that our F be consistent, so we'll say our F of X vector here. Okay. For this problem, one thing could be just FG plus FT plus FS. Right, so that's just the definition of the raw total amount of muscle force. So you take each muscle force and you just add them together. And so through our optimization algorithm, what we're going to do is we're going to minimize this guy. So I chose this one for our first objective function because we can actually kind of solve this by hand. And so I'll kind of show you kind of the process that that you would go through to solve this equation by hand. Okay. Any questions on how we set this up so far? Okay. All right, so now that we have all three things defined, and so we have our design variables, we have our constraint, we have our objective function, now it's time to start guessing. Okay. And so again, if you use MATLAB for this, MATLAB has a much more sophisticated way to guess. It's not just going to be random guesses, which is kind of what we're going to basically be doing. But there's kind of smarter ways to do it. Okay. And so I'm going to do 3 guesses here. And so for each of my 3 guesses here, I'm going to assume that only one muscle acts and the rest of the muscles are 0. Okay. All right, so let's do a first guess where only the gastrocnemius muscle is going to act. Okay. So if only the gastrocnemius muscle are going to act, then FT is equal to 0 and FS is going to be equal to 0. Okay, and so that's two of our muscle forces already. Right, and then the last equation that we'll use to solve for the gastrocnemius muscle is our constraint. Okay. So our constraint, once again, is 100 is equal to 0.039 FG plus 0.008 FT plus 0.036 FS. Okay. So remember, the definition of the constraint is that no matter what combination of muscle forces that we compute, this equation must always be satisfied. Okay. We already know from this guess that FT and FS are going to be 0. And so I'm going to just set those equal to 0 right away. Okay. And then we're going to solve the rest of the equation for FG. Okay. And so FG here is equal to 100 divided by 0.039. And so if we perform that division, we get 2,564 newtons. Okay. And so with that, we have solved for the basically the design variables under this condition here. Okay. And so we know FG, we know FS, we know FT. And so now that we know the design variables, we can compute our objective function. So our objective function fx is equal to ft plus fs plus fg. Okay, we know these two are 0. And so our objective function is 2,564. Okay. Okay. So that's kind of one iteration. And so that basically gets us, it gets us a candidate solution, and we found one that satisfies our constraints, and we computed the objective function at that location. Okay, so I'm going to do the same thing, but I'm going to do it for the other two situations. So in situation 2 here, let's assume that we have only tibialis posterior muscle. Okay, and so if the only muscle acting is tibialis posterior, that means FG is equal to 0, FS is equal to 0. Okay. And if we come back to our constraint here, okay, and so 100 is equal to 0.039 FG plus 0.008 FT plus 0.036 FS. Okay. We know that under this case, FG and FS are equal to 0. And so that means FT is simply going to be 100 divided by 0.008, which is equal to, I'll go on my calculator because I don't have it in my notes. It's equal to 12,500 newtons. Okay. All right. So once again, under this second case here, this is like our second guess, our second this set of design variables, our second candidate solution. Okay. And so if we evaluate our objective function here, we just add up these three. And we get our objective function is 12,500. Okay. And so if you compare that to our previous objective function, so for our first guess, we got an objective function value of 2,564. Okay. And remember, we want to minimize the objective function. And so based on that, which one of these gives us a better solution? First one, right? And so the first one right now, first one is leading the way. And so our second guess didn't turn out good. Okay. And so right now, our first guess is better than our second one. Okay. Let's do one more. One more guess. And our third guess here is going to be the soleus muscle only. So that means FG is equal to 0, FT is equal to 0. So let's again apply our constraint. And so I'm just going to go at a time. Okay. And so according to our constraint, FS is going to be equal to 100 divided by 0.036. So I'll put that into a calculator. We get 2,777.78, repeating, of course. Okay. Let's compute our objective function. And so under the third guess, our objective function, much better this time. We get 2,777.78 for our objective function. But once again, if you compare this to our first guess is still superior because it has a lower objective function. Okay.
Sorry, Professor. So you're saying
Yep.
the goal is to have a low objective function.
Wait, say again?
Is our goal to have a low objective function?
Yes, our goal is to have as low an objective function as we can. So we want to minimize that based on our candidate solutions. Okay. Right. And so that's, we've basically performed an optimization by hand. And so, this is a very simple example. And so we did a very simple objective function that we can compute by hand. And actually has a very simple result that, that you could have solved for actually without optimization. And so basically the muscle with the largest moment arm, that's going to have the lowest amount of force needed because that's, we're doing our optimization based on the moment. Okay. So unfortunately, it's going to be a long break before we see this again, because on Thursday we have the midterm exam. And so we'll pick this up after Thanksgiving. And so after Thanksgiving, I'll do a good recap so you kind of remember this, because I know there's a lot of details today. But what we'll see after Thanksgiving is that depending on the objective function, you can get different results. And we'll talk about some smarter objective function that you can specify in these sections. Okay. All right, and so probably I might not get a chance to say this to you on Thursday. You'll probably be upset with me on Thursday anyway because of the midterm exam. But let me say it now. Hope you guys have a wonderful Thanksgiving holiday. I know it's kind of late in the semester, and so after it's going to be a sprint. But hopefully you guys take the time to kind of rest, enjoy time with friends, enjoy time with family. If you're going out of town, I'm wishing you all good travels and all that stuff. And so I'll see you for the exam Thursday, but I want to make sure I say that before we go. So thank you guys for coming today. I'll see you guys Thursday for the exam, and then of course after Thanksgiving as well. Okay. Yeah. No, we're not. So there's no more homeworks after all. So after the midterm exam, I just want you guys to focus on the final projects. Yeah.
Will the midterm format be similar to the first one? Just like a few for response, then 2 or 3
Exactly.
actual solving? Okay.
Exactly. It'll be exact same format. So there'll be 4 short answer questions and 2 problem solving questions. Yeah.
Sick. Thank you.
Yes. Yeah. So
Basically, the muscles would be set of criteria for this.
exactly. Yeah. So 1E, 1B on the homework. I anticipated us getting a bit further for that homework, but those last 2 conceptual questions are based on this.
I got 1B, but.
Oh, yes. Yeah.
I had a couple. So
Yeah.
for homework, on 3, so it's probably more for the midterm, obviously. So noticing on the solution, the FX will always be negative. And I was also realizing that after you solve for the acceleration of X direction, this will become negative.
Yeah.
So then that's why we did negative.
Exactly.
Okay, that's why you wrote it that way.
Exactly. Right. So the negative comes out as a change.
Yeah. The time derivative.
Exactly.
And then, so the work like this is fine. So what I did was I found the equations, and then I solved the acceleration, and I just took the point. I don't want to.
Yeah. That's perfect. You can do that for the it's too much, right? So once you solve the accelerations, you can just plug it in.
Yeah,
That's fine.
And then I watched the video today. You talked about the equation, the angle,
Yeah.
the rotation. So I did it a little bit different. I did it in class. You showed like that big, like it was a 3x3 matrix that had a bunch of like sign, a bunch of symbols.
Yeah.
And that's what I used. So like I solved like for sign.
So the one we did in class, that was for a 3D. That was for a 3D. But this is technically 2D. So actually the only rotation matrix actually is from right here.
Yeah.
And we kind of augmented it with kind of the extra. So I know there's been a little bit of confusion on it. So for a 3D case, the way that we would augment it is actually 4x4.
Yeah.
And so for this one, you would just use these two, and you would use just the transformation matrix.
Which is the video.
Exactly.
Kind of getting a close in.
Okay, I think there is some overlap on that. So I think on the 3D one, there's like one. I think it actually corresponds to this as well. Actually,
I think I accidentally got the right answer, but I'm gonna just focus on the other one.
Exactly. Yeah. I mean, for the exam, it's gonna be.
Yeah.
Yeah.
Part two, or sorry, problem 2, part 4.
Yeah.
So it's multiply the matrices,
Exactly.
multiply them, and then we're using 2D to get an angle. right?
Exactly, right. Yes.
So I did that by using the inverse cosine on the position 1,
Yeah.
inverse cosine on the position 1, 2,
Yeah.
do inverse sine.
Yeah.
But the inverse cosine, I get like 115 degrees. And then the other three, I get 64.95.
Yeah, so for that one, so the 111, because the magnitude, the position of the minus sign is going to affect things.
Yes.
But so if you notice, you take 180 minus the 100.
Oh,
End up
yeah.
with 65. So that's fine. It's just kind of where you're kind of measuring the other from.
Okay.
And so that's how you can kind of check. So I mean, you can check and see which one you get kind of the same 3. So 3 you get the same one. And the one will be 180.
Okay, so that makes sense.
That's perfect.
All right.
I saw your email, the update for the our project.
Yeah.
We were able to find a different idea.
Okay.
So it's gonna be like crewing while we're doing this.
Okay.
Has anyone taken that?
No one's taking that. So yeah, I think that'll.
Okay, that'll probably be a lot better.
I think so too.
Yeah,
You'll find a lot more. I was mostly concerned about the sources.
Yeah, I think we were looking at it also, and we're like, no, we don't really see that many sources for that either.
Yeah, but I think there's gonna be a lot more.
Okay.
That's been studied.
That's probably been studied. Yeah. All right.
Yeah, I think that's much better.
Okay. All right. Sounds good. Thank you.
Yeah.
For 4A, how do you help me out? Figure out one again. Oh, I had a very, so this is a fix.
Yes, it's a pin. So the rotation is free on this one,
Oh,
but
that's
only the transverse is constrained. So we have D1Y and theta 1 both 0. But
Yeah.
for node 2, only D2Y is both 0. But theta 2 is still free.
That's
And so
why I was
this,
confused on
and
why.
so you're gonna read this the same here. It's still gonna be 0 on the, there's no moment, but you can still solve the rotation.
So I actually did do that and it did. So I figured that'd be the case. But I got it. Really
Yeah, so then, the F should be there. Try, I might have flipped the sign on that one. I don't remember if it was this one or the other one, where I made the positive button.
So this. Your magnitude are still wrong.
Tell me look at his phone.
0.03.
Look at your phone.
I'm getting. Oh, I got 0.03 here. Yeah, it's just my answer for data 2.
Oh, that one?
For this.
That's the only one we need.
It's just as, if you round up, that's 0.03.
I have to take it care of.
Oh, yes.
Yeah, no worries. If you take a screenshot,
Okay, sure.
But the setup works mostly, that's how they assemble. So you want 2 nodes, 2 elements right after each other. That's where that. It's just something in the middle.
Okay.
Yeah, I would double check all the uses. think all the units will go. But yeah, it would probably be something.
So that's a 166, so that's
Yeah,
really
that's fine.
But that's for.
0.5.
Yeah, maybe
Maybe I made an error there.
I would double, I can double check for you though, so if you send it to me, I'll double check all the.
Alright, I'll double check for the last time.
So I'll send him, I mean, I'm not studying, we help on this, because the things I got.
Okay. Yeah, so I was gonna say that, I didn't realize it until this morning when someone came to my office. But 3B is actually, so that was an old exam problem. And so on the exam, obviously I can't ask you guys. Software solutions. So that was just like a setup problem. I didn't realize it until I signed it for homework last year, that if you actually try to solve it, then you get a single matrix. I don't see that on my math app though, because I've actually fiddled with my math app settings so that the precision is best. And so I can actually, but that's actually what it's for. Yeah, I don't know what it is.
So what I'm hearing is don't do it.
You should still set it up, but don't worry about this. Yeah, I'll make it.
Yeah. So I just wanted to ask, how come for all of these, why we have to use, how come we put in our origin here and not like on the row?
That's just convention how we augment the matrices. So we kind of put it over. Yeah, it's just in theory, yeah, you can put it down there too. But I think just how it's defined.
That's just our
Oh,
old,
we also
I
explained
think
why-
old lab.
In the notes.
I get a
um,
12,000%
that
error.
Z vector
Yeah,
was
that's right.
0, 0,
That's the
1.
lowest.
Yeah,
but then
today.
somewhere else it said it was RX, RY.
The Z vector. So this is a 2D problem. So the Z vector is just coming out of the page. And so the only Z vector that you can there is to take the cross.
It's hurting kind
And so after you find, like, you take
But I don't
the
know
difference
if I've
between the
ever
two
hurting
points,
crap and no crap.
that's how you find the X axis, right? And
No
then to
crap.
find the Y axis, you need to find something that's
No
perpendicular.
Yeah, so here it was XY1,
Yes.
X2B, and that's what I plugged in, I plugged in the fixed one for XY1.
Yeah.
But then I saw it in the notes, 0, 0, 1, it's like the. That's what I was just.
That might have been a
Basically,
cross.
what we're trying to figure out is about how come we're multiplying by our Z direction here, but then. So the actual matrix is made out of the X, Y, and Z component, right? That's what makes up this matrix.
So for 2D, it's actually only two. So there's X and Y, X and Y, and X and Y. So there's no Z component at all because it's purely 2D.
Right.
So the only time the Z comes in is when you're taking a cross product. So you need to take a cross product between two vectors. And so in order to find cross product in 2D, you need to kind of make a phantom vector. Because the cross product only works.
Okay, I see what you're saying. It's just very confusing as well, the way that, the truth be told, I had a friend explain them over to us. And,
Yeah.
if I'm being honest, I just didn't really understand what he was doing. So he did was he basically, he normalized the vector and then he multiplied that by, what he said, the Z.
Yeah.
The Z vector, so that's why.
Yeah. Yeah, that was the cross product I was talking about. So you find the X axis, that's something that you normalize. And then the Y vector from there is you take a cross product between your X vector and a Z vector that comes out of it. Because you want to find something, because the Y axis has to be with the X. And the only way that you can find that is through a cross product.
Gotcha.
Yeah. And that cross product, and because when you take a cross product with two vectors, the result is another vector that's perpendicular to both. And so the only direction that's going to be perpendicular to X, but still be in the XY plane has to be the Z vector.
So that's why I have to do the cross vector with it too.
Exactly.
Okay, that makes a lot of sense.
Never mind.
And then for numericals, like, is it like kind of, I know this is not so yet, is it kind of safe to say? It's mostly the mix.
Yes.
They can be X,
I don't think I even have it in for sign. I would just say, just to kind of explain how you do it. So.
Oh, yeah, so we don't have to write with further.
If what do you mean inverse time? You mean inverse time? Inverse-
Yeah.
I probably agree.
Oh. What are we talking about?
We're
Like,
asking
for the
about.
exam.
Oh, yeah, for the exam. I'm not going to have you do any inverse sign or inverse cosine. There will be an inverse dynamics problem and an inverse kinematics problem. No heavy calculations. That's this.
Okay.
Human motion.
And then there's also gonna be, 8? Is that all like the
Um,
steps and the?
That will be there, but not in problem solving form, so you should
So
understand more
four.
conceptual.
Can you disclose how many files all pushes we're gonna get?
There's one, risk on kinematics is 1%. So exactly how it's.
And then the rest just. Okay, so can you tell us like which example?
That's already one. That's already one. Yeah.
To tell us exactly what it is. Just give me the exam right now.